So we are here, right? Yeah. And this is the Gulf for the that I'm not familiar because I know that we have people from different parts of the world. So if you look at this background figure, you see a number of hurricanes that usually approach the Gulf. And either it's tropical cyclone, hurricane, typhoon. It's just depending on the basin. It's just similar concept or the same thing. So as a result of the number of hurricanes we usually receive in the Gulf, it is essential for us to improve how we model them, how we how our model are working in terms of their predictions on both winds and waves. So if you look at the historical hurricane in the Gulf, I have their the legends here from tropical depression to category 5, which is from less than or equal to 70 meter per second to 70 meter per second or greater. We have 110 storms within 2010 and 2024 alone, in which 46 are within the category 1 and 5, which are extreme hurricanes. And averagely, annually, they cause 60 injuries, 70 deaths, and 54 billion in economic losses. So as a result of these catastrophic damages that usually cause, it is essential and imperative for us to improve how we forecast them and how we monitor them. And wind wave surges are some of the leading causes of most of the damages, although we also have compound flooding. So on Monday, I pick up this figure from NOAA Hurricane Center, and on Monday, they showed that this is their prediction of Hurricane Erin. The first side of this coin is the first 3 days prediction, and the last part is the last 2 days, which makes 5 days prediction. And you can see that as we go in time, the cone is increasing, which is showing that the uncertainty in the models that they are using in terms of predicting the hurricanes. And just imagine we shift this towards the continental United States. We are talking about several states in which they are not sure either the hurricane is going to make landfall at this point or at this point. So, and it leads to the question that even with the computational resources we have, why are we still having this kind of uncertainty in hurricanes? Now, the reason is that hurricanes are very complex and they engage almost the first layer of the atmosphere, and also they engage the surface ocean. And they involve a number of interactions. We have the atmospheric side, we have the oceanic side, we have the wave interaction. And if you have to make a prediction, each of the model that's making specific prediction, either waves, wind, currents, or even ocean temperature that control the fluxes between the ocean and atmosphere, each one of them has to make very accurate prediction, which right now it's still very difficult for us to have models that can do that. And even essentially, we don't have compound coupled modeling framework where we can put all this model together. So most of the times we just parameterize some of the main processes and we give the model to give us very good results, which is impossible. So one of the things that we use to force the model, we make use of global wind data sets, especially for many of the models, either circulation model, wave model, surge model. So yeah, I'm trying to show the performance of some of the these global data sets during some of the hurricanes. So I have ECMWF here. HRR is high resolution rapid refresh. ECMWF is a forecast 9 kilometer, which is also okay. HRR is 3 kilometer and does not cover the whole Gulf. And we have R5, which is a reanalysis of the CCMWF, and we have Copernicus data set, which is another improved data set. And I have the VMAX of observation and VMAX of all these models. And you can see that most of the times, especially during the hurricanes, they have very high biases. And the implication is that if you are using them to forecast wave or forecast circulation, you'll be getting like low values, especially during extremes. And I look at several hurricanes, Ida, Grace, Elaine, and Milton. And one peculiar thing that you can see with Hurricane Milton is that most of these models, they miss both the track and the intensity of Hurricane Milton. So what we are trying to do is that when we know that most of the models, they show strong biases during hurricanes, and we can either correct these biases, and also we see that most of the problems are around the vortex of the hurricane, and we can also find ways of correcting the vortex. So either we use some simple approaches or we use numerical models. And if you have to use numerical models, we need a lot of computational resources. So this is my workflow for improving the wind in a nutshell. I take the one of these global data set. Either I apply this parametric approach, which we just remove the vortex of the hurricane and we replace it by a parametric equation, which are based on like some statistical data that have been collected on hurricanes. So another approach is to use bias correction, in which we know that they don't get the bias, they underestimate most of the wind, then we can just increase some of the high winds. And either we also use a numerical model, and we're also using WRF for this study. The WRF that we are using, we set the model in which we have 9 kilometer, 3 kilometer, and 1 kilometer grid. We also try 900 kilometer, and we use several physics. But the approach for modeling is it's the same in the sense that you get your grid, and the grid is just like a computational framework where the model physics are calculated. Then we interpolate all the initial condition and boundary condition on the grid, and we apply the physics of the model. For WRF, which is an atmospheric model, it's more complex in the sense that we have to apply both the physics of the model, and also we have to consider dynamics. But for wave model and ocean circulation model, we usually make use of the physics alone. And most of the data sets I've gotten from NCAR, they provide like a very strong framework where we can just pull out the data set of the initial and boundary condition and use it to force the model. So for the wind correction, as you can see, the approach is just to take the wind at a particular threshold where we know that the model, they start underestimating, which I didn't show you in one of our previous work. But you have to determine which threshold you have to use. Most of the results that we had earlier showed that around 15 to 17 or 20 meters per second, that's where the underestimation starts. So we pick the threshold and we use this bias in which we just correct the tail of the distribution. And it's very simple. We don't need like more computational resource, but we notice that if we use this method, sometimes it also increases the high winds when the hurricane is just forming. So we are trying to see a better way that we can use this method. For Hurricane Helene, it performs well, and we see that it follows the high wind follows the distribution of the hurricane as well, which is very good. But also from the previous, you also see that we see this up and down movement, which goes with the input data. So it depends on the wind input that we use. But for Hurricane Milton, you can see that it performs very bad. So aside, is there also some other methods that we've tried to use this method, this approach, and just correct the biases, but still they show the same trend. So aside this method, we can also use parametric approach, in which we just remove the vortex around the hurricane and we replace it by parametric. And the concept is that we can delineate the hurricane wind, the vortex, into the rotational part and the translational part, and we can use simple, atmospheric equation, just that we just make use of like the pressure gradient, and we balance the forces, and we find our rotational aspect of the equation. So this method is just like we try to improve the rotational aspect or the vortex of the hurricane. But the problem is that if we do this beyond the edge, as you can see that it is like an exponential equation and it becomes zero away from the vortex. So we need to find a way of merging the background wind, which is like era 5 or whichever wind we, and then we just merge it with the parametric wind that we just used, which is what I'm showing here. And we have a workflow for that also. It's very simple. It's simple, more complex than the previous approach, and it gives better result than the previous approach. So but there are some things that we need to do because we have to blend them out. We have to find where we have to start the blending, and we have to also develop equation in which they can transform properly from the background wind towards the parametric wind. So the wave model that we use, they are called spectral models, and they just compute the evolution of wave action or wave spectrum over time. And we have different part of the model. This is the left side of the model. So the concept of this modeling framework is that whenever we have new physics, we can just put it on the right side and we see how that affects the evolution of the spectrum or evolution of the energy. So for wave models, there are several physics. We have the input that controls the wind input. That's what's going from the wind towards the wave. And we have the dissipation. We have the nonlinear interaction, which is quite complex. It controls interaction between 4 waves or 3 waves. And when we get to the coastal area, we also have bottom processes. We have friction, depth breaking, and triad interactions. So for my own research, I focus on both the one that controls the input and dissipation, because traditionally people believe that the wind transfer energy to the waves and the wave dissipate, and they've been coupled from there. So whenever we are trying to improve wind as a result of we know that there are biases. We can just improve the wind. We can improve the wind equation and see how the dissipation also changes. So as I said, that we see that winds, they have like very strong biases. One of the ways that wave modelers use in the past is to control some of the equations that control the wind input. So you just like try to increase this particular variable, and that increases the input that's going into the model without reducing the dissipation. So my own aspect of the work is to improve how this is done. And I try to bring in some equations to improve the stress so that we won't be just making use of like wind input without having interaction between the wave spectrum, and the wind stress that's being computed. Also, I try to improve the dissipation, which I'm not going to go into this. So this is the workflow of this. And it's also similar to the work in which we create the grid and we interpolate our data on the grid, the initial and boundary condition, and we set up the model physics, and we run the model and we validate the model. So I'm not using data simulation in this work because I'm trying to improve the wave, the physics of the model. So if I use data simulation, I'm just trying to kind of tune it towards observation, which doesn't make any sense. So I'm trying to improve the physics, so I'm not using any data simulation. And most of the because of the nature of the work I'm doing, I have to make use of many programming languages, because most of the models are written in Fortran, either Fortran, MATLAB, Python, to get the initial and boundary condition, and also to analyze the data at the end of it. So this is how the unstructured mesh look like, which is what I'm using. The reason being that when we look at if you have to make use of structured grid, especially for the Gulf, for instance, we have like 18 to 32, which is like 14 by maybe 20. So if we use structured grid of, let's say, 1 kilometer, then we'll be having like more than 10 million nodes. But we can make use of unstructured grid where the places where we need higher resolution, very close to the coast, we can increase the resolution. And offshore area where we have less processes that are occurring, we can just make the resolution very low in that region. And you can see the mesh, and you can see the transformation of the mesh. This is one of the reasons why this is one of the aspects where Python is meeting up with MATLAB, because most of these software were initially done in MATLAB, and recently they are trying to, we've been trying to write it back to Python. So this is my validation process for the paper I wrote last time. These are the buoys. Unfortunately for us, we that are studying hurricanes, we don't have enough data set, which is the irony. So we never have enough data set, because most of the observations, they don't work during hurricanes, or we just don't have enough. But recently there have been a number of observations that have been collected around the track of the hurricanes, which I'm trying to get to validate the model. But we see this is satellite track, and these are the buoys during Hurricane Ida. And only 2 or 3 buoys are very close to the track of Hurricane Ida. Most of them are just away from the track. But I was able to use satellites to add to the data set for the work. And if you see, this is some of the physics that I'm trying to put into the model. And we could see that the model is performing in terms of bringing in this new physics. This is the wave height, this is the peak period, and this is the mean wave direction. But also during 42084, which is very close to Hurricane Ida, the buoy that captured that particular wave shut down, and we could not really get the maximum wind of Hurricane Ida. So we are not sure what the peak of Hurricane Ida was. But if you look at other buoys, we see that the physics that we are trying to bring into the model are really working. So
you have like maybe a couple more minutes.
Just one, yeah, just like
I see the many slides.
So I just try to get some new data set from, but I realized that there are some new data. So with this wind improvement method that I'm trying to use, I'm trying to bring in all this data set, and I just added this, just that if you look at this plot, you could see that the wind are getting to 0 meter per second sometimes, which is quite non-physical. So anytime we get data, observational data, it's essential that we check them to see what's wrong with the data before we even try to put them into machine learning model or any other thing. Because as Ruth said earlier, the uncertainty in the data, we have to be very aware of them. I think that's my last slide. Sorry for I have to walk through but the pipeline and the research itself. I'm sorry for that. Thank you.
Any questions for Hafeez?
Yeah.
So, in my understanding, one of the big challenges with hurricanes is the eye wall replacement cycles. So I wonder if you, like your modeling, incorporates that, or is that coming from different models?
So for the weather research forecast model, the atmospheric model, they incorporate that physics into the model. But see, if I show the result, which you spend a lot of time running the model, setting up the model, but sorry. But it hasn't given it gives us very good result for Hurricane Helene, but it does not give us very good result for Hurricane Ida. It missed the track of Hurricane Ida, which I'm trying to see how to improve that in the model. But for the simple models like the linear method, the parametric method, they don't include that. It's just like, let's get the wind, let's improve the tail of the distribution, or let's get the wind and let's just improve the vortex around the wind. They don't consider the old equation of the atmosphere.